Hello, this is Dr. Salil. Welcome to today's lecture on heat exchangers. In this session, we are going to discuss different types of heat exchangers and also introduce the concepts of overall heat transfer coefficient and fouling of heat exchangers. A heat exchanger, which is denoted by HX in short, is a device which is used to exchange heat between a hot and a cold fluid. The intention of designing a heat exchanger can be either cooling a hot fluid or heating a cold fluid. At the same time, these fluids are not allowed to mix. This means that they will be flowing in separate channels which are bounded by walls so that they do not mix. The applications of heat exchangers include household heaters, air conditioners, refrigerators, chemical processing units, power generation systems, automobiles, aircrafts, and many more. A household air conditioner or refrigerator typically has two heat exchangers, the evaporator and the condenser. Similarly, the radiator in an automobile is a typical heat exchanger. As we have just mentioned, in a heat exchanger, the hot and the cold fluids will be flowing in individual channels separated by walls. This means that there will be heat transfer within the fluids by means of convection and also heat exchange through the walls by conduction. This means that we cannot describe the heat transfer rate by means of a single parameter like the thermal conductivity or the convective heat transfer coefficient H. So instead, we use an overall heat transfer coefficient, which is denoted by U, to describe the combined effect of convection and conduction. The simplest type of heat exchanger is what we call as a double pipe heat exchanger. As the name indicates, it's made of two concentric pipes. One fluid will be flowing through the inner pipe and the other one will be flowing through the annulus between the inner and the outer pipes. This is shown in the diagrams given below. The double pipe heat exchanger can be of two types based on the direction of fluid flow. If you see the diagram on the left, the hot fluid is flowing in the inner pipe from left to right. The cold fluid enters here. It is also flowing from left to right and leaves here. So that means both the hot and the cold fluids are flowing in the same direction. This is what we call as parallel flow. If you look at the temperature variation of a heat exchanger with parallel flow, it will be as shown in the diagram here. The temperature of the hot fluid is shown by the pink line and that of the cold fluid by the black line. So the hot fluid enters at the left end. As it flows, its temperature is reduced because it is losing heat to the cold fluid, and finally it leaves the heat exchanger at a lower temperature. The opposite effect is seen in the case of the cold fluid. It also enters at the left side. Its temperature keeps on increasing as it receives heat from the hot fluid, and finally it leaves at a higher temperature at the right side. The other possible configuration is one in which the fluids will be flowing in opposite directions. This is what we call as the counterflow. So here you can see the hot fluid is still moving from left to right, whereas the cold fluid is moving from right to left. And here is the temperature variation for the counterflow heat exchanger. As in the previous case, the temperature of the hot fluid is decreasing and it is flowing from left to right. But the difference is the cold fluid is entering at the right side, its temperature is increasing and it leaves on the left side. An interesting feature here is that the temperature of the cold fluid cannot exceed that of the hot fluid at any point in the heat exchanger. This is because it is precluded by the second law of thermodynamics, specifically the Clausius statement, which tells us that the heat cannot flow from a cold fluid to a hot fluid without any external interference. If the cold fluid line has to cross the hot fluid, it means that there has to be some heat exchange from the cold to the hot side, which is not possible. The best that can be achieved in a heat exchanger is that both the fluids can come out at the same temperature. The same holds good for the counterflow. At any point within the heat exchanger, the cold fluid always remains at a lower temperature compared to the hot fluid. But it is possible that the exit temperature of the cold fluid can be higher than the exit temperature of the hot fluid without violating the second law of thermodynamics. This is possible only in the counterflow mode. An extension of the double pipe heat exchanger is what we call as the shell and tube heat exchanger, which is most commonly found in stationary applications such as industries. It is of a heavy and bulky construction, so it's not suitable for mobile applications. As the name indicates, it is made of several tubes which are enclosed in a shell, and one fluid will be flowing through the tubes and the other fluid will be flowing in the shell which is surrounding the tubes. We can see the diagram here. These are the tubes which are carrying one fluid which is shown by the pink color, and the space between the tubes is shown by white color, that is the shell. The axis of the tubes remain parallel to the shell axis. Can have a large number of tubes, even in a few hundreds. This increases the area of heat transfer, and we can achieve a large amount of heat transfer within a given space. So again, as we can see, the tube fluid comes in here. This area is called as a header. The header collects the fluid, and from here it opens out into the tubes, and the fluid is flowing through the tubes. It comes out here, and there is another header here where the fluid gets collected, and then it leaves from the header. The shell fluid comes in here and flows around the tubes and leaves at the other end. These plates that we see here are called baffles. Baffles direct the shell fluid around the tubes so that we get more effective heat exchange. Without baffles, the shell fluid may have a tendency to go straight out here like this without contacting a lot of the tubes over here and here, which will in effect reduce the area of heat transfer and reduce the heat transfer rate. But we can see that the baffles prevent a direct flow of the shell fluid. Instead, it takes a more circuitous route like this, flows around the tubes, and finally it will come out here. So this improves the contact between the shell and the tube fluids, and therefore improves the heat transfer rate. The baffles are attached to the shell, and they carry holes through which the tubes are inserted. So that way they also lend a structural support to the tubes and help in maintaining uniform spacing between the tubes. As I mentioned, the header collects the tube fluid at both the inlet side and the outlet side. This is helpful because this way we can have a single inlet point and a single outlet point for the tube fluid, even though we have a number of tubes. This also helps in the maintenance works because we can unscrew or detach the header at either end, and that provides access to all the tubes, which helps in cleaning the tubes, etc. Another way of increasing the heat transfer rate is by making the fluids to move back and forth within the heat exchanger a few times. This is what we call as a multi-pass heat exchanger. Each time a fluid moves from one end to the other, we say that it has completed one pass. So if it takes a turn and returns, it can make an additional pass. In all the examples that we have seen till now, we had single pass heat exchangers. But if we look at this diagram here, the tube fluid comes in here, it goes to the other side, that makes it one pass, then it takes a U-turn and then it returns to the same side, so that makes it two passes, one pass here and one pass at the top. But the shell fluid makes only one pass. It comes in here at the right side and goes out here on the left side. So this is a one shell pass and two tube pass heat exchanger. In the second diagram here, we will again look at the tube fluid. It comes in here, makes one pass, returns, that is two passes, again takes a turn, comes to the left side, so that is three passes, and then takes a final pass here. So it is four passes for the tube fluid. The shell fluid enters here. There is a plate here which prevents the direct flow of shell fluid from the top to the bottom. So the shell fluid is also directed from the right side to the left side. So that gives it one pass, and it goes through the space here to the right end again, making it the second pass. So we have a two shell pass and four tube pass heat exchanger here. As we have discussed earlier, the quantity of heat transfer increases with the area of heat transfer. So typically heat exchangers are designed maximizing the surface area available for heat transfer. This is usually quantified by using a term called as the area density, denoted as beta, which is the ratio of the heat transfer surface area to the volume of the heat exchanger. So this should have a unit of 1 by meter, but since it's a ratio of area to volume, it is typical to use a unit of meter square per meter cube. If the heat exchanger has got an area density greater than 700 meter square per meter cube, it is termed as a compact heat exchanger. Some examples are car radiators, which have beta of the order of magnitude of 1000 meter square per meter cube. Stirling engine regenerators have beta approximately 15,000 meter square per meter cube. One of the most effective heat exchangers is the human lung, where the beta is as high as 20,000 meter square per meter cube. The key to increasing the area for a given volume is to use thin plates or corrugated fins, which enhance the area but don't contribute to the volume. So these plates or fins are a common feature in all the compact heat exchangers. You can think about a car radiator. There are a lot of very thin fins which you can observe in a car radiator, which enhances the heat transfer rate. Another characteristic feature of a compact heat exchanger is that it employs what we call as a cross flow. Unlike parallel flow or counter flow, where both the fluids will be flowing along a common axis, in cross flow the two fluids will be flowing perpendicular to each other. Some examples can be seen here. We have a tube fluid flowing along the tubes and the external flow across the tubes in both the cases here. But there are two classifications possible here, which are unmixed flow and mixed flow. The mixing here of course does not refer to the mixing between the hot and the cold fluid, because that is precluded by the definition of the heat exchanger, but it refers to the freedom of a fluid to deviate slightly from its intended direction of flow. We'll explain that with the help of these two examples. In the case of unmixed flow, one or both the fluids will move only along the intended flow direction. This is of course true for the tube fluid, because the tube fluid will always flow along the tube. It does not have a freedom to move in any other direction, but the possibility of the deviation occurs for the external flow. In this case, for the external flow, these fins or plates are provided which allow the external fluid to flow only in the left right direction. They don't allow the fluid to move along the tubes, that means perpendicular to its intended direction. So we say both the tube flow and the external flow are unmixed in this case. In the second case, we can see that the tube fluid is exactly the same as in the first case, but there are no external fins or plates, which means that the external fluid has got a freedom to move to the left or to the right. So that makes the external flow mixed and the tube flow unmixed. These are some common designs of compact heat exchangers. As we can see, they employ different types of fins here. In the first case, it uses plate fins with rectangular flow passages. This again is with plate fins and circular tubes. Here also you have got tubes, but the fins are of the circular or annular type. These are corrugated fins. This is a single pass heat exchanger and this is a multi-pass heat exchanger. Because of the extremely close spacing of the fins, the flow passages are very narrow, which makes the flow laminar in many of the cases. A laminar flow has its benefit in that it does not have too much of pressure drop compared to a turbulent flow. This allows the use of a pump of smaller capacity to circulate the fluid. On the other hand, the heat transfer coefficient is also small for the laminar flow, so the reduction in the heat transfer coefficient has to be compensated by increasing the area available for heat transfer. The plate and frame heat exchanger or plate heat exchanger shown here is an extension of the concept of the compact heat exchanger that we have seen earlier. Here the fluids will be flowing in individual corrugated flat flow passages. So there will be hot fluid flowing through one plate which contains this corrugated flow passages, and the hot fluid will be flowing in neighboring plates which has similar passages. We can see that in this particular case the fluid represented as A is the cold fluid. It comes in here at the bottom, flows here, it will travel through these plates, rise to the top and go out on the top. The B fluid is the hot fluid which enters at the top. It also has specific plates for traveling, and as it loses heat it will become more dense, it will tend to fall and it will flow out here at this end. So we have alternate plates for the hot and the cold fluids, so that each hot plate is sandwiched between two cold plates and vice versa. So these plates are shown for illustration alone. This is a cold plate where the fluid is gaining heat and rising from the bottom. So the pipes of the inlet and the outlet of fluid A are connected by the plates shown like this, which have the up arrow. Likewise, the hot fluid in the top and the bottom tubes are connected by the plates with a lighter shade which have the down arrow. These plates are all stacked as shown at this end. This is actually how it will look in the real case. Here some plates are removed to show how the direction of flow looks like. One benefit of the plate and frame heat exchanger, apart from its compactness, is that it is of a modular nature. We can increase the heat transfer by adding more plates. We can always extend this further to increase the heat transfer. And this is most commonly used for liquid streams which have nearly equal pressure. A regenerator is a heat exchanger which is characterized by the fact that the hot and the cold fluids alternately pass through the same flow area. That means a certain portion is exposed to hot fluid for some time and then to the cold fluid, and this keeps repeating. So first, as the hot fluid flows through the regenerator, it loses some heat to the regenerator and comes out at a lower temperature, but in that process the regenerator gets heated up. Next, as the cold fluid flows through it, the cold fluid gets heated up, but the regenerator gets cooled down and is now ready to receive the hot fluid again, and the cycle goes on. So this means that the regenerator has to be a porous medium, because then only it can allow the fluids to pass through. Also, it should have a high heat storage capacity. That means the product of its mass and specific heat, so that it can carry a large quantity of heat. A typical example of such a material is a ceramic wire mesh, which is commonly used in Stirling engines, etc. So there are two types of regenerators: a static regenerator like the one used in Stirling engine. The regenerator itself stays still, but it is alternately exposed to the hot and the cold fluid. Another type is a dynamic regenerator, which is usually of a rotating drum type as shown in this diagram, so that each portion will in turn pass through the hot and through the cold fluid. We can see that here in this diagram. If you look at certain portion of this one, the cold air is coming in here, passes through the regenerator and passes out here, so that will reduce the temperature of the regenerator. As the drum rotates, it will then come into contact with the hot fluid, that is the hot exhaust. So the exhaust gases pass through the cold regenerator now, and it will get cooled down, but the regenerator itself gets heated up, and then it goes up again to receive heat from the cool air. So that is a rotary regenerator, which we also call as a thermal wheel. So in this slide we will define the overall heat transfer coefficient, which is used to describe the combined effect of convection and conduction. This discussion will be applicable to both double pipe and shell and tube types of heat exchangers. For the definition, we will assume that the hot fluid is flowing within the tubes and the cold fluid is flowing outside the tube. So it is shown here diagrammatically, and a cross section is shown below. So we have the hot fluid, which is having convection, and then there is a wall which has conduction, and the cold fluid, which is again having convection. Using electrical analogy, we can define the thermal resistances for all the three modes of heat exchange. On the inner side, where the hot fluid is flowing, the convection resistance is given by 1 by HI AI. For the wall, the conduction resistance R wall is given by the logarithmic formula for the cylindrical systems, expressed in terms of the outer and inner diameter, thermal conductivity, and the length of the heat exchanger. For the outside, we again have the convective resistance in terms of the heat transfer coefficient HO and the surface area AO. The inner area AI and the outer area AO are expressed as pi dl. In case there is a radiation occurring, the heat transfer coefficient H is defined so as to include the combined effect of convection and radiation. So for convention, we can write the heat transfer rate as a ratio of the overall temperature difference, that will be Ti minus To divided by the total resistance, that is the sum of the three resistances, the inner convective, the wall conduction, and the outer convective resistances, since they are in series. So delta T by R is the heat transfer rate Q dot. Now we will define the overall heat transfer coefficient, which will be analogous to the Newton's law of cooling. So we can express the heat transfer rate as the product of the overall heat transfer coefficient U, the surface area A, and the same temperature difference delta T. So which area has to be used? We can either use the inner area or the outer one. So we will be having an overall heat transfer coefficient with respect to the inner surface area or with respect to the outer surface area. If we compare the expressions here, we will find that UA is 1 by R, or in other words 1 by UA will be the resistance R. Again, from these expressions it is seen that the overall heat transfer coefficient for the inner surface UI will have a greater value compared to UO, because UIAI has to be equal to UOAO, but since AO, the outer surface area, is greater, the overall heat transfer coefficient UO has to be lower than UI. Next, we look at some approximations and some special cases with respect to the overall heat transfer coefficient. In most of the heat exchangers, the conduction resistance of the wall is negligible. This happens when the wall thickness is extremely small, or when the thermal conductivity of the material of the wall is very high, which is normally the case, so that we can neglect the conduction resistance compared to the convection resistances. So if we consider a wall of a very low thickness, we can say that the inner and outer surface areas are roughly equal. That makes the overall heat transfer coefficients with respect to the inner and outer sides also nearly equal. So if you look at the previous expression here, if AI and AO are approximately equal, and the conduction term becomes negligible because DO and DI are also equal, so that the conduction resistance becomes 0. The total resistance will be 1 by HIA plus 1 by HOA, since AI and AO are both the same. So that way our overall heat transfer coefficient will be defined by this expression. Here HI and HO need to be determined using the appropriate Nusselt number correlations. HI will be determined based on the Nusselt number correlation for flow within a tube, and HO for flow within an annulus. Again, from this expression we can see that if one heat transfer coefficient is much smaller than the other, for instance assume that HI is much smaller than HO, then 1 by HI is going to be much greater than 1 by HO, and this part can be neglected, which means that the overall heat transfer coefficient will be approximately equal to HI, which is the smaller of the two heat transfer coefficients. That means that the overall heat transfer coefficient is primarily decided by the lower convective heat transfer coefficient. A good example of this is a case where one of the fluids is a gas which has a low heat transfer coefficient, and the other is a liquid which will be having a higher heat transfer coefficient, so that the overall heat transfer coefficient will be equal to the heat transfer coefficient for the gas side. And as we have seen in the discussion on fins are commonly used on the side which has got lower convective heat transfer coefficient. So if we have a gas to liquid heat exchange, we use the fins on the gas side. But then if we are using fins, we have to account for the surface area of the fins as well. For the fin surface, the total surface area becomes sum of the finned and the unfinned areas in the ideal case, if the entire surface is at the same temperature. But since the temperature varies along the fin, we have to use an effective area for the finned surface, so that will be given by the product of the fin efficiency and the actual finned surface area. So this will be the formula to be used for the area of a finned surface. Some representative values for the overall heat transfer coefficient are shown here. You can see that the value of U depends on the nature of the fluid. For example, if you have got water, we have got typically values around 1000 watt per meter square degree Celsius. But for the case of gas to gas heat exchangers, the value is very small, because as we have seen, convective heat transfer coefficient will be smaller for gases. Also we can see that for cases where there is a phase change, like in a steam condenser, we have got a much higher value of the overall heat transfer coefficient. Next we look at the concept of fouling of heat exchangers. In the previous discussion on overall heat transfer coefficient, we considered convection in the fluids and conduction through the walls. This is an ideal case. What happens with prolonged use of heat exchangers is that some particles get deposited on the tubes and the other heat transfer surfaces. So these deposits have additional conduction resistances, which increase the overall resistance and therefore reduce the heat transfer rate. So we need to study what are the causes of fouling and how to account for the effect of fouling in the calculation of heat transfer rate. Some of the main causes of fouling are denoted here. When hard water containing salts and minerals is employed in a heat exchanger, over a period of time, these particles will get precipitated on the pipe surfaces, resulting in fouling. This can be eliminated to a large extent by appropriate water treatment like softening of the hard water. Wherever exhaust gases or flue gases are used in a heat exchanger, such as in air preheaters, boiler tubes, etc., the ash present in the flue gases will tend to get deposited on the heat transfer surfaces. A third cause is chemical reactions occurring at the heat transfer surfaces, which result in the products accumulating on the surface. A very good example is the formation of rust and other forms of corrosion on metallic tubes. Remedies for chemical fouling will be to use glass coatings or to use plastic pipes, etc. In addition to increasing the resistance, chemical fouling such as corrosion will also often result in a reduced life of the heat exchanger. A fourth cause is biological fouling. This is usually attributed to the growth of algae in warm conditions. This can also be eliminated by chemical treatment of the water. Of course, all the heat exchangers are cleaned periodically to clean the heat transfer surfaces and to keep fouling under control. This diagram shows the fouling of superheater tubes in a boiler by the deposition of flue ash. Now we will look at the fouling factor, which is a term used to represent the effect of fouling on the resistance of a heat exchanger. Fouling factor, denoted as RF, represents the resistance per unit surface area caused by fouling. So whenever we are designing a heat exchanger, we need to incorporate this factor also, because that will help us in estimating the amount of heat transfer in the long term. This means that when we are including the effect of fouling, we will be having a greater amount of resistance, and therefore we will have to design a bigger heat exchanger for the same amount of heat transfer rate. Fouling is found to be the effect of fouling is more pronounced at higher temperatures and at low flow velocities. This is because high temperatures enhance the chemical reactions, algal growth, etc., which we have seen are some of the prime causes of fouling. Also, at low flow velocities, the deposits will tend to stick to the surfaces rather than flow along with the fluid. At high velocities, they will tend to get carried away with the flow. So here we discuss the calculation of the overall resistance and the overall heat transfer coefficient, including the effect of fouling. So the R now includes the convection on the inner surface and the effect of fouling on the inner surface. RFI is a fouling factor for the inner surface, since it is a resistance per unit area and the actual area on the inner surface is AI. The resistance due to fouling will be RFI by AI. Please remember that even though RFI is the fouling per unit surface area, it needs to be divided by the area and not multiplied by the area to get the actual resistance. This is similar to the concept of the thermal contact resistance, which we had seen in the discussion on conduction. And then we have got the conduction resistance for the wall. This is the fouling resistance on the outer surface. RFO is a fouling factor for the outer surface. AO is the corresponding surface area. And the last term is the convection on the outer surface. 1 by HOAO is the convective resistance for the outer surface. So we now have two additional terms here denoting the fouling of the inner surface and the outer surface. So as we can see, that is going to increase the overall resistance and it is going to reduce the overall heat transfer coefficient U. Some representative fouling factors are given here. Here again we can see some interesting facts, such as the effect of temperature. We have seen that at higher temperatures the effect of fouling is more, that is denoted by the difference in the fouling factor for the two temperatures here. Also, in cases where there are more chances for sediment such as fuel, oil, we have a higher value of the fouling factor RF. So that brings us to the end of this lecture. Thank you for listening.